Hi guys, welcome back to my channel. As you might already know, in my previous video, I shared a step-by-step guide on building a basic drone with Pixhawk autopilot using 450 mm frame. The response from all of you was truly awesome and I am genuinely glad for your support and feedback. Today I am crafting a drone that weighs less than 2 kg. Throughout this video, I will guide you step by step process that will help you to build your own Pixhawk drone that fit within the all-up weight of 2 kg. Understanding the components needed to build a drone is crucial before we start assembling. Let's discuss each component starting with airframe. Airframe is the physical structure of the drone that provides the framework for all components to be mounted. It comes in a various size and material, and for our project I am going to use lightweight carbon fiber frame along with aluminum mount. The total weight of the frame is around 450 grams. Next, motors. Motors are the driving force of the drone responsible for spinning the propellers and generating lift. Selecting the right motor is essential for achieving the desired performance. Here I am using Sunny Sky 380 kV motors. The weight of the motor is 100 grams including cable. Then electronic speed controller. An ESC is an essential component that controls the speed of each motor and ensures smooth and precise movement. This device receives signal from the flight controller autopilot and regulate the power going to the motors. I have Hobby 4-in-1 ESC and its weight is 21 grams. Then propellers. Propellers are crucial for generating lift and propulsion. Choosing the right propeller size and pitch is important for the drone stability and efficiency. I have 13-inch nylon propellers and its weight is just 21 grams. Next, autopilot. Autopilot is the brain of the drone responsible for flight control, stability and navigation. Pixhawk is a popular open source flight controller known for its reliability and flexibility. I am going to use Pixhawk autopilot to provide precise and stable flight characteristics. Its weight is about 91 grams including mount along with the dampers. Next, GPS unit. A GPS unit is essential for accurate positioning and navigation. It allows the drone to maintain its position, follow waypoints and execute autonomous flight missions. I am going to use here GPS module and its weight is 49 grams. Next, power module. The power module is responsible for measuring the voltage and the current from the battery. It provides variable information about the battery status and help us to monitor power consumption during flight. The weight of the power module is 16 grams. Then telemetry radio. Telemetry radio enables communication between drone and the ground control station. It allows us to receive real-time data and telemetry such as altitude, battery voltage, number of satellite count, GPS location, distance to home, total distance traveled and flight time. I have Wi-Fi telemetry module from CUAV and its weight is just 5 grams. Then radio controller. The radio controller is the handheld device used by the pilot to control the drone. It transmits command to the drone through receiver. It enables manual control and overriding autonomous flight modes when it is required. I have a 16 channel FR Sky transmitter, and I have RX8R receiver, and the weight of the receiver is just 14 grams. Now that we have a clear picture of the component, let's roll up your sleeves and get started with building our lightweight Pixhawk drone. I am excited to share this journey with all of you. Let's start. Next, I am flashing firmware and going to do calibration. Please check my previous video, link in the description. I explained all type of calibration which is required for Pixhawk drone. First flight setting for autopilot based drone. To set up your quadrotor for his first flight, follow these general steps. Always keep in mind that the specific details might vary depending on your hardware and software versions. So, always refer to the official autopilot documentation and the manufacturer's instructions for your drone components. Now, I will provide a general outline to get you started. First one, battery setting. Second, motor setup. Third, adding filters. And finally, setting up the initial PID. First one is battery setting. Configuring the battery setting for your quadrotor is to ensure safe and efficient flight operations. The battery setting in quadcopter primarily involve setting the battery capacity, voltage and current sensor calibration, and low voltage cutoff parameters. Then battery capacity. In the mission planner, go to full parameter list or full parameter tree. Look for the parameter named battery capacity. Set this parameter to the total capacity of your drone battery in milliampere hour. For example, if your drone battery capacity is 5000 mAh, so you have to set 5000. Then voltage sensor calibration. Your flight controller may have an onboard voltage sensor which is connected on it. Calibration ensures accurate reading of the battery voltage. For many modern flight controllers, the voltage sensor calibration is automatic and you don't need to perform it manually. However, it's essential to double check it. Then, current sensor calibration. If your flight controller has an onboard current sensor, or if you have an external current sensor which is connected, you may need to calibrate it for accurate current readings. Then, low voltage cutoff setting. This low voltage cutoff setting is to prevent over discharging your battery, which can damage it and reduce its lifespan. The low voltage cutoff will vary depending on the type of battery which you are using. For example, lithium polymer or lithium ion. So always refer to the battery manufacturer's manual for the safe voltage range. Then battery low voltage setting. Set this parameter to the voltage at which you want to trigger a low voltage warning. Then fail-safe battery voltage. Setting up this parameter to the voltage at which you want the flight controller to initiate a fail-safe RTL action due to low battery voltage. This value should be lower than battery low voltage. Then motor setup. Configuring the motor setting for your quadrotor is to ensure that all the motors spin in the correct direction and at the proper speed. First one is motor order. First, ensure that the motors are correctly connected to the corresponding motor output on the flight controller. Different frames and different flight controllers may have different motor layouts, so make sure you have the motors connected in the right order. Then motor direction. Confirm that each motor is spinning in the correct direction. In the quadrotor, the motor on the front left and rear right side should spin clockwise direction, and the motors on the front right and rear left side should spin counterclockwise direction. If any motor is spinning in the wrong direction, you can usually reverse the motor direction. Then propeller installation. Ensure that the propellers are installed correctly on the motors. Each propeller should be securely attached and facing the correct direction. Then motor parameters. Quadcopter allows you to configure specific motor parameters to match your quadrotor's hardware setup. These parameters can be adjusted using Mission Planner. First one, motor PWM minimum. This parameter sets the minimum PWM value for the motors. The value should be set that the motors spin at ideal so that quadrotor is stable without lifting off on the ground. Then motor PWM maximum. This parameter sets the maximum PWM of the motors. The value should be set that the motors reach full throttle without overloading them. Then motor spin arm. This parameter sets the spin up speed of the motors after arming the quadrotor. Then motor spin minimum. This parameter sets the PWM value at which the motor will spin during arm. It should be slightly higher than motor PWM minimum. Then motor spin arm. This parameter sets the it should be set the value slightly higher than motor PWM minimum. Then motor testing. Before your first flight, perform a motor test to ensure all motors are spinning correctly and responding to the throttle inputs from your handheld transmitter. You can do this in the motor testing section in the mission planner. Then finally, ESC calibration. Some electronic speed controllers may require calibration to ensure that they recognize the minimum and maximum throttle values correctly. Then filters. Filters are used to process sensor data and reduce noise, which ultimately improve the accuracy of your flight controller measurements. Configuring the filter setting for your quadrotor is an important step to ensure stable and smooth flight. First one is INS gyro filter. This parameter controls the gyro filtering in the inertial navigation system. Lower value allows for more noise in the gyro reading but increase the responsiveness. If higher value smooth out the gyro data but may introduce some lag in the quadrotor response. The default value set to 20, which is a good starting point for most setups. Then INS Axle filter. It is similar to the gyro filter. This parameter controls the accelerometer filtering in the inertial navigation system. The accelerometer filter is responsible for fusing the accelerometer data with the gyro data to estimate the quadrotor's orientation. The default value is typically set to 20, which is suitable for most setups. Then INS notch enable. This parameter enable or disable the dynamic notch filter. The dynamic notch filter automatically detects and filter out gyro and accelerometer noise at a certain frequency. If the dynamic notch filter does not adequately address vibration or noise issue, you can manually set the notch frequency and notch bandwidth using the parameters INS notch heads and INS notch bandwidth. Then setting up the PID controller for your quadrotor is essential to achieve stable flight and responsive controls. The PID controllers are responsible for stabilizing the drone and maintaining its desired orientation. First, understand the PID controller. Before, when you start tuning the PID parameters, it is crucial to understand the purpose of each controller. First one is proportional. It provides a correction based on the current error. Then integral. It accumulates the past error to eliminate any steady state error. Then the proportional controller, which might not address. Then derivative. It predicts future error by measuring the rate of change of the error, and it helps dampen oscillation and improve responsiveness. Then first set the flight mode. Choose a flight mode to tune the PID values. The most common mode for tuning in stabilize mode. This mode provides basic stabilization and is suitable for initial tuning. Then start with default values. Quadcopter firmware usually comes with stock PID values that work well for most setups. Start with the default value and perform test flight to observe how your quadrotor responds. If it's relatively stable, you might not need any excessive tuning. So that perform test flights. Fly your quadrotor in a safe and open area. Observe its behavior during different maneuvering such as hovering, forward flight, turning. Let's start with some tuning process. If you notice during the test flight any issues in test flight, you can start tuning the PID values. Always keep in mind that tuning process is an iterative process. Let's start with proportional tuning. First, increase the p value if the quadrotor feel sluggish or unresponsive. Decrease it if you notice any oscillations or instability. So increase the p value if you feel sluggish or unresponsive. Decrease the p value if you notice any oscillations or instability. Then integral tuning. Usually the item to reduce steady state error. If the quadrotor drift slowly, then you can increase the I value to compensate that. Finally, deturning. The D-term help dampen oscillations and improve responsiveness. If your quadrotor shows any oscillations, try increasing the D value to dampen that.
ఫోన్